This is lecture 8 in our series of videos on introductory quantum computing. So last time we started talking about quantum circuits. So somehow in analogy with the circuit model of computation, quantum circuits, again, you are constructed in terms of a bunch of gates that act on a set of qubits instead of bits. So a classical circuit is sent in some bits, and then there were multiple transformations happening here and there. And ultimately, the bit string for, let's say, n bits gave, as a result of the computation, a bit string for L bits. So there we could copy classical bits. So we had these fan-out operations. But quantum mechanically, we can't do that. So essentially, we have, in a quantum circuit, we have n qubits coming in. And then there's going to be a whole bunch of operations that occur. So let's say that entire thing, which right now I treat as a black box, and then we start talking about it more, is a quantum circuit. N bits, and the system really has n qubits. So at the end of the day, after all these operations, we have n qubits. So what the quantum circuit does, it takes a state in the 2 to the n by 2 to the, in the 2 to the n dimensional Hilbert space of n qubits, and maps it to another state in the same space. Of course, we can maybe forget about some of these or perform the measurement on just a subset, but generally a quantum circuit, you can think of it as a big unitary transformation on the state of these n qubits, which can be a big superposition. Now, we don't, in the same way that, you know, we constructed the classical circuits in terms of elementary gates that act maybe on 1 bit at a time, just maybe flip it, or act on 2 bits at a time, or sometimes 3 bits. A quantum circuit also is typically decomposed and is constructed in terms of a bunch of elementary gates that at a given time act on 1 qubit, act on 2, maybe act on 3. So you have, maybe I take an example, I send in 5 qubits. So I have a system that has 5 qubits. So maybe first I act with some unitary here, and then I don't do anything to the other guys. So there's going to be these 2 guys have a 4-dimensional Hilbert space, 2 to the power 2, but the entire system has a 32-dimensional space, 2 to the 5. So when U acts here on these 2, it does whatever it does, and then there's going to be identities acting on the other guys. So nothing happens to them, so they just go through. So let's call this, I don't know, Q1, Q2, Q3, Q4, Q5. So I have 5 qubits in my system, and there's going to be a circuit that changes this 32-dimensional vector of these 5 qubits, and it has a decomposition in terms of a bunch of gates. So let's say there's some unitary operator acting here, we call it U12, and then maybe there's another thing that acts on 2 and 3, for example. Then maybe there's another one that acts on 1 and 4. So 2 just goes through. There's something that acts on 1 and 4 here. So let's call it U14. And these can be various operations. And then maybe there's something on 3 and 5 or something. So 3 just goes through here. 1, 2, 3, 4. Yeah, let's say we put some other gate acting on 3 and 5. So again, something couples these guys. So U3, 5. So 4 is going through. I have 1, I have 2, I have 3 that's going through here. So that's an example of a circuit. We have a bunch of gates. These are only 2-qubit gates. They act at different, they couple different qubits at a time. So how do we combine these? So what is the net effect on the Hilbert space of these 5 qubits? Well, first time, so suppose I'm constructing that basis in terms of the computational basis that has the tensor products of 0 and 1 for 1, 0 and 1 for 2, 0 and 1 for 3, 0 and 1 for 5, 0 and for 4, 0 and 1 for 5. So the first one, when it acts, it's going to be let's say a 4-dimensional matrix that acts on these two, and then I have a whole bunch of identities acting on the other guys. So there's going to be an identity acting on qubit 3, an identity acting on qubit 4, an identity acting on qubit 5. So these identities are 2-dimensional each. So the net result is going to be a 32-dimensional unitary operator that acts on all of these. So it acts trivially on these. But then after U1, 2 acts, then U3 acts. So U2, 3 is going to be an identity acting on 1, and it gets tensored with this 4-dimensional operator 2, 3. And then there are identities on 4 and 5. So then again, this guy becomes a 32-dimensional matrix, and it keeps acting. So if I don't have things that are, I don't have qubits that are decoupled, essentially, ultimately, this will act or transform the state in the entire Hilbert space. Suppose, for example, Q5 never coupled to anything. So maybe there was just a single qubit gate acting on Q5. So there's nothing that entangles it. So maybe we can treat that separately, but that's the general structure. And then of course this keeps going. So I would play the same game for U1, 4, U3, 5, etc. So that's an example of a quantum circuit. It takes in a 2 to the n dimensional vector for n qubits. It performs a bunch of operations in terms of some standard gates that you would build that couple maybe 2 qubits, sometimes maybe 3 qubits. We always have single qubit operations. And then the net result is going to be a transformed state, a mapping of the full state to something else. So that's something that encodes a quantum computation. And then we're going to perform some measurements and extract, some useful information from that final state. But now let's try to work a bit more simply. Let's try to get a little bit more practice with gates. So we started by just mentioning some single qubit gates or single qubit unitary operators last time. So there were 6 of them. That there was the X, the Y, the Z. Then we had the Hadamard. We had the S or phase gate, and then we had the pi/8 gate. So we had a bunch of single qubit gates. These are some 2x2 unitary operators that act on 1 qubit and transform its state, which is a vector in a 2-dimensional space. Then there's another very useful class of unitary matrices that are used in quantum computing, and those are rotation operators. So we need a little bit of mathematical background to introduce them properly. So these are, so let me rewrite the X, Y, and Z operators. X was 0, 1, 1, 0. Y is 0 minus I, 0. And Z is 1, 0, 0, minus 1. And we can easily check that these are unitary. So for example, if I calculate X dagger, I have to take the complex conjugate, but it's real, and I have to transpose it, but it's symmetric, so it's going to be the same thing. And then X dagger is equal to X dagger X is equal to 0, 1, 1, 0 times 0, 1, 1, 0, and that's going to give me 1, 0, 0 times 1 plus 1 times 0, 1 times 0 plus 0 times 1 again 0, and then 1 times 1 plus 0 times 0, 1. So that's the identity. We can do the same thing for Y, for example. Then Y dagger is going to be 0 I. 0 minus I, right? So Y transpose is going to be 0 I. Then, yeah, Y transpose is going to be 0 I. And we have minus I here, but then we have to take the complex conjugate. So Y dagger is the same as Y. So these are so-called Hermitian matrices when the dagger, the complex conjugate and transpose is the same. So then again, Y times Y dagger is equal to Y dagger times Y is equal to 0 minus I, 0, 0 minus I, 0, and then I have I times minus I gives me 1. The off-diagonal terms become 0 for a similar reason. And here I have an I times minus I. So that's, again, the identity. So these are also unitary matrices. Now, there's a whole class of single qubit operators known as single qubit rotations that are defined as an exponential of X, Y, and Z. So let me first write it, and then we try to make sense of what they mean. So let me write Rx of theta. This is defined as e to the minus I theta over 2 times x. So theta is some parameter, some angle, if you wish. I is I. And this, if you think about spins, this encodes a rotation by angle theta around the x-axis. It's an operator that generates that rotation. But we don't need to worry about that interpretation in terms of spin. So this is, we're just doing quantum computing. So we have just a model for qubits, and this is some particular and useful transformation on qubits. So this notation may not be familiar. So what does it mean? What is the exponential of a matrix? So we know what the exponential of a number is, but X is some matrix, is some operator. It's a 2x2 matrix. So what does that mean? So let me write the other expressions. Again, they're completely analogous. So we have an Ry of theta, which is e to the minus I theta over 2 times y, and Rz of theta, which is e to the minus I theta over 2 times z. Okay. So the way these are defined is through the Taylor expansion. That's one way to think about it. So take the function e to the x. So this is little x, not that operator. just some number. So if I think about the Taylor expansion of e to the x, it's going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. That goes up to infinity. Maybe as a reminder, so if you have some function f of x, and you're interested in approximating that function around x naught, well, so this function, maybe has some shape here. So I can, maybe the 0th order approximation is, I assume, like, look at the value of the function there and just imagine something that's a constant. So that's just matching the value of the function. So I can write f of x as f of x naught approximately, and very close to x naught, that's probably decent. But then you can say, well, what if I match both the value and the first derivative? So I can do, so here x naught seems to be the minimum. Let me pick a different x naught to make the point better. Or change the shape of the function a little bit. So the function does something like this. So now we can say, well, yeah, so what the one approximation is this, you just go through. So you just consider a constant function that matches the value at x naught, and very close to x naught, that's going to be close to this function. Or you can match the first derivative. So that's going to be a tangent to this f of x. And the way we match the first derivative is I do f prime, the first derivative calculated at x naught, and multiply that by x minus x naught. So if I now take the first derivative with respect to x and then insert the value of x naught, well, this gives me 0, it's a constant. X minus x naught gives me the derivative of 1, so I find this. So then at x naught, I've matched both the value and the first derivative. And then we can keep going with this. So if I can say, well, I want to match the value, the first derivative, and the second derivative. So I do the second derivative of f calculated at x naught, and I multiply that by x minus x naught squared over 2 factorial. Now you can see if you take the first derivative, so this goes away, this becomes f prime of x naught. This becomes, this 2 cancels the 2 factorial, this becomes f double prime, the second derivative, times x minus x prime, x minus x naught. And then if I take another derivative, I get rid of x minus x naught. I kill that term because I lost the x. So this matches first and second derivative. And then you can play this game. You can go to infinity, really. So that's the Taylor expansion. So if a function has an infinite number of derivatives at some point, then it can be approximated by an expansion like this, cubed over 3 factorial. Now, so this Taylor expansion for e to the x, because the derivative of e to the x is just e to the x, the derivative doesn't change. And if I consider x naught equal 0, so I Taylor expand e to the x around x equals 0, then all the derivatives are going to be e to the x, and then e to the 0 is 1. So all of these f prime, f double prime, triple prime, they're all 1. And then x naught is 0. So that's the expansion I get. Now, so I can think about the exponential of a matrix in the same way. So if I have now a matrix can think about e to the a, the exponential of that matrix, or any function of that matrix in general. One can think about Taylor expanding that function, looking at that structure, and then replacing this multiplication or these powers by matrix multiplication. So this can be thought of as identity plus a plus 1 over 2 factorial a squared plus 1 over 3 factorial a cubed, 4 factorial a to the 4th, etc. And then these powers of A are defined through the standard matrix multiplication. So A squared means matrix A, matrix multiplied with matrix A with itself. Okay, so now how do we make progress on these particular rotation matrices for those particular X, Y, and Z operators? Well, so let's think a little bit about this. So consider e to the I, so let's say Rx of theta, it's e to the I theta over 2x. Okay, so let's take a look at what these are. So x is x, and then I'm going to get, so let me write this. So I'm going to get identity plus I theta over 2x plus 1 over 2 factorial I theta over 2 quantity squared times x squared plus 1 over 3 factorial I theta over 2 cubed x cubed cubed, etc. Now there's a nice simplification. So if I calculate x squared, as we said, it's going to be, because x is both Hermitian, it's its own Hermitian conjugate, and unitary. So this was equal to the identity. So that means all even powers of x are equal to the identity, and all odd powers are equal to x. So this gives a big simplification. So from here, I find identity plus, let's factor out the identity from all the even powers. So this is going to be identity times 1 plus I theta over 2 squared plus, well, 1 over 2 factorial, 1 over 4 factorial, I theta over 2 the 4th, all the even powers, plus x, all the odd powers. So I theta over 2 plus 1 over 3 factorial, I theta over 2 cubed, etc. So it turns out that this is the Taylor expansion of cosine theta over 2. And this is I times or minus, oh, well, we wanted to maybe define this with a minus I. Let's see. Yeah, so the rotation, the standard convention is to define it with the minus I here. So here I have minus I theta, minus I theta, minus I theta. So let me put these minuses here. So this is cosine theta over 2. And this is minus I sine theta over 2 times x. So one way to think about it is, if you consider like e to the I alpha, right, is going to be cosine alpha from I sine alpha. And then the Taylor expansion should match, but cosine is an even function of alpha, so it only has even powers. Sine is an odd function of alpha, so it only has odd powers. So then when you combine like all the terms with an I, you're going to factor out the I and get a sine, and the terms that don't have an I, which are even powers, because when you square I, you get -1. Those combine to give us the cosine. So these are respectively the Taylor expansions of cosine theta over 2 and minus I. If I factor out the minus I, this is a Taylor expansion of sine theta over 2. So in this case, this exponential is quite simple. So this is a unitary that's cosine theta over 2 times I minus I sine theta over 2 times x. And then if I combine them, I find cosine theta over 2 on the diagonal. And remember, x had 1s on the off diagonal, so it doesn't contribute to the diagonal. So I get minus I sine theta over 2. So that's a very useful unitary transformation. We can check again that it's unitary more explicitly. So let's check the unitarity of Rx theta. So it has that form. So R dagger x theta, I have to take the complex conjugate, which means change the I to minus I, and I also need to take the transpose. So, but it's symmetric, so the transpose is not going to do anything. So this becomes cosine theta over 2, I sine theta over 2, I sine theta over 2, cosine theta over 2. And then R dagger R, we use a shorthand notation. So for cosine theta over 2, I put C. For sine theta over 2, I put S. And then here, R has C on the diagonal minus IS on the off diagonal. So what is this? So here I'm going to get C squared. I times minus I is 1, so I get plus S squared. Here I get minus ICS plus ICS, so that's 0. Again, here I get plus ICS minus ICS, 0. And again, I get S squared. I times minus I is 1 plus C squared. So sine squared plus cosine squared is 1. So that's the identity. One can check that R dagger R is also similarly the identity matrix. So let's push this a little bit so we can do the same thing for Ry theta, which is e to the minus I theta over 2 the Y matrix. And this, so again, it's the same idea that Y squared is the identity, so we can play the same game. So that becomes cosine theta over 2 times the identity minus I sine theta over 2 times the y matrix. And that becomes cosine theta over 2, cosine theta over 2 on the diagonal. On the off diagonal, I get minus I, no I rather. So y already has a minus I times minus I is minus 1. I squared is minus 1. So that gives me minus sine theta over 2. And here I get sine theta over 2. And similarly, RZ of theta, which is defined as minus I theta over 2z, is cosine theta over 2 I minus I sine theta over 2 z. So that's going to be a diagonal matrix. So I'm going to get cosine theta over 2 minus I sine theta over 2 on the diagonal, off diagonal 0, 0, cosine theta over 2 plus I, right? I have a minus 1 in z, minus 1 times minus I is plus sine theta over 2. We can also write this as e to the minus I theta over 2 combining these, and e to the plus I theta over 2. Okay. So far we talked a little bit about just the general structure of a quantum circuit. We focused on a bunch of single qubit gates that would appear in a quantum circuit. So these don't couple any different qubits. We had a little bit of detour talking about how to exponentiate a matrix, and we needed that to introduce these rotation gates that are quite commonly used in quantum computing. And then let me state a theorem. So one reason these rotations are very useful is that they can provide a decomposition of any unitary operator for one qubit. So there's a very useful theorem. And it's called the ZY decomposition. So it says consider an arbitrary 2x2 unitary matrix. So we call that U. So there's some arbitrary unitary matrix, it's 2x2. Then the statement is that there are real numbers alpha, beta, gamma, delta, such that U is equal to e to the I alpha, so that's just a scalar. Then RZ beta, RY gamma, RZ delta. So up to an overall scalar e to the I alpha, we can write any unitary as a product of three rotations. One, first you rotate around Z, then around Y. So we have one of these RZs, one RY, and another RZ for three different angles. So how can we make sense of that? Well, the idea is that, you know, if U is unitary, it's some 2x2 matrix. It's going to have columns and rows that are orthonormal. So let's talk a little bit about that. So let's say U is U11, U1 first row, second column, U21, U22. Right. So what we're saying is that U dagger is equal to U dagger U is equal to the identity. So that means that, let me write U dagger. It's going to be U11 star. I'm taking the complex conjugate and I'm taking the transpose. So then I have U21 star here, U12 star, U22. And if I look at, for example, U dagger, what do I get? So I have U11, U12, U21, U22, 21 star, 12 star, 22 star. So here I should be getting 1, but this 1 is also U11 absolute value squared plus U12 absolute value squared. So if I think about the first column, or the first row rather, that row, if I think of it as being a vector, it's normalized as length 1. Then now if I do the first and second, I find U11 times U21 star, U12, U22 star. So let's write that out. It's 1, 1, 2, 1 star plus 1, 2, 2, 2 star. So that's like, so this element here, one can think of it as the inner product of the first column, or the first row rather, with the second row. So then it means this row has length 1 and it's orthogonal to this row. So because that has to be 0. And similarly here, we're going to get the length of this row. So each row interpreted as a vector has length 1 and is orthogonal to the other row. So that comes from U dagger being the identity. And then U dagger U being the identity tells us the same thing about the columns. So when you have these two elements that when you take the absolute value and square it and you add them up, they add up to 1, you can always interpret the absolute value as the sine and cosine of an angle. So each row must be sine of one angle, cosine of another angle, and then they can have some phases. But then we can make sure that that each row is orthogonal to the other row, and each column is orthogonal to the other column. So if you think a little bit about this, there's only one way to construct this arbitrary unitary. So here, so for example, suppose I have some phase e to the I something whose absolute value is 1, and that has the general structure of e to the I times some real number. So I need to, let's say, put cosine gamma over 2 here. And then this row, again, must be e to the I some stuff. Something. This must have a sign because the length of that row must be 1. So absolute value this squared plus absolute value that squared must be 1. So this is also e to the I some stuff sign. Now this column must have length 1. So again, this is e to the I some stuff sine of the same angle over 2. So that the column, so absolute value of this squared plus absolute value of this squared is 1. And similarly, this column or this row must have norm 1. So this is cosine gamma over 2. Some stuff. Now we want to guarantee that essentially this row is orthogonal to this row is orthogonal to this row, and this column is orthogonal to that column. So what I can do is maybe I can put a minus sign here. It doesn't matter, right? So it's like an e to the I pi, right, is a -1. So it's kind of convenient to pull it out. Let's say here you have some angle phi 1, 1, you have some angle phi 1, 2, phi 2, 1, phi 2, 2. You have some angles. Okay, so if now this row is orthogonal to this row, what is the inner product? Well, I have to take the complex conjugate here. So I'm going to get e to the, let's say, minus I phi 1, 1 plus I phi 2, 1. Then you have a cosine gamma over 2, a sine gamma over 2. Then when I multiply these, I have to take the complex conjugate of the top one. I have a minus sign, e to the minus I phi 1, 2 plus I phi 2, 2, then the product of sine and cosine. So then if this is 0, then this means that this phase and that phase are the same. So that means phi 2, 1 minus phi 1, 1. So this phase minus that phase must be the same as phi 2, 2 minus phi 1, 2. So let's call the difference of that beta. They must be the same. So essentially, I can think about phi 2, 2, phi 2, 1 is beta plus phi 1, 1. And similarly, phi 2, 2 is beta plus phi 1, 2. Okay. So we do that. Then we can ensure that now, so this was for the rows, we can place the same game for the columns. And then we see that then this minus this, so 1, 2 minus 1, 1 must be the same as 2, 2 minus 2, 1. So then again, they have something added to them. That's the same. So these constraints essentially restrict the form of this unitary to be e to the I alpha minus beta over 2 minus delta over 2 cosine gamma over 2 e to the I alpha. So I want this phase to have a beta added to it. So this should be plus beta over 2. The rest must be the same. I have minus, so here now I want to add a delta to this phase and a delta to that phase. So alpha minus beta over 2. Now this is minus delta over 2. I have to add plus delta over 2. And then you have a sign. And here, again, I want to take this phase and add a delta to it. So it's going to be e to the I alpha plus beta over 2 plus delta over 2. So essentially, we found that we found this difference to be beta, this other difference to be delta. They have to be the same. That's the only thing we know. We give it a name. And then what remains is phi 1, 1. So we need like one angle. So one angle, because I know if I have this, then I know this. And I know this in terms of gamma and beta and delta. And then I also know this. So I know all of them. So there's only one free parameter. So we make these shifts. So these are symmetric. So that alpha corresponds to that one free parameter. And this form is exactly what we wrote. So this is e to the I alpha, RZ beta, RY gamma, and RZ delta. So these rotation matrices can give us any 2x2 unitary. Okay, so in the last few minutes, let me briefly introduce control gates. So these are the simplest control gates are 2-qubit gates. So what they do is they act on, let's say, the second qubit if the first qubit is 1. So let's write the simplest control gate is a controlled NOT or CNOT. And it looks like this. So that's the notation. Essentially, it's a control X, right? Remember, X flips, X changes 0 to 1 and 1 to 0. So we want to write a gate that changes the second qubit, flips the second qubit only if the first qubit is 1. Okay, so let's call this CNOT acting on, and then it's going to be again some matrix for the 4-dimensional space. So then it acts in interesting ways in superpositions. So on part of the superposition where this one is 1, it flips the part corresponding to this guy. And in parts of the superposition, when this one is 0, it doesn't do anything. So if it acts on 0, 0, well, what will it give me? Well, the first qubit is 0, so it doesn't do anything. Should give me 0, 0. If it acts on 0, 1, again, the first one is 0, so it should give me 0, 1. If it acts on 1, 0, it should, the 1 doesn't, nothing happens to 1, but it controls the second one. So this 0 flips to 1. And if it acts on 1, 1, similarly, that goes to 1, 0. So now that's how this operator acts on the basis states. Then I can extract how it acts on general superposition. So then I can represent it like this. So I can write CNOT as a matrix. So acting on the first basis state, which is 1, 0, 0, 0, it just gives me the same, which is 1, 0, 0, 0. So it must have a 1 here. And nothing else. Now, again, for the second one, it acts like identity on the second one. On the third one, which is 1, 0, it changes it to 1, 1. So if you think about this row, acting on 0, 0, 1, 0 should give me 0, 0, 0, 1, which means it can only have 1, 1, but it should be in the fourth position. And then here, when it acts on, so let's consider a row that acts on 0, 0, 0, 1, it must have a 1 here. So that's a representation of this 4-dimensional operator on the space of 2 qubits. And it's a simple example of a control gate. So one of the qubits controls what happens to the other qubit. So I think this is a good place to stop. We'll continue this discussion in the next lecture.